In this video, I'm going to briefly introduce Simon-Markov process and the limit theorems. A Simon-Markov process is a generalization of continuous time Markov chain. In continuous time Markov chain, the surgeon time must be exponentially distributed. But in Simon-Markov process, the surgeon time can have any distribution. Let's consider this example. So S0 and Si are two states. One is disease-free and one is infectious disease. There can be transitions between these two states, and for each state, it has its own surgeon time distribution. They does not have to be exponentially distributed. The formal definition of a Simon-Markov process requires the introduction of a bivariant random vectors. So here S is the state space, Yn is the state at the nth transition, and Sn is the surgeon time for the nth transition. A history of this Simon-Markov process is given by at each transition what is the state and what is the surgeon time. Given this history, we can calculate the probability that state I is going to state J within x units of time. So given this history, it has a Markov property that this probability only depends on the state of last transition. This Gij is called the kernel of the Simon-Markov process. It is very essential to define this process. So what we can get from the kernel G? First of all, we can get the transition matrix for the embedded discrete time Markov chain. It is simply by taking the time in Gij to be infinity. And second, we can get the surgeon time distribution for state I. It is by summing over all the states that I can transit to. And the third is the conditional surgeon time distribution. It's actually combining the first two. What it is given that the state I is going to transit to state J, what is surgeon time? So this formula is obtained by the Bayes law. This is some simple results we can get from Gij. Let's move on to the limiting theorems. One of the important limiting theorems is the limiting recurrence time. So here let Bt denote the time until next transition for time at time t. So the limiting distribution of Bt, if we are given that at time t, the system is in I, then it is defined as here. We calculate that, and it will be given by this equilibrium distribution. So an equilibrium distribution in the renewal process is defined in this way, with this Hi be the interarrival time. So for this limiting theorem to be true, there are some requirements. One is that the embedded discrete time Markov chain must be ergodic. The second is that this process must be regular. We don't want the expectation renewal time to be infinity. Another important limiting theorem is to discuss the distribution of states in the long time. So what we are interested is first this limiting probability of state J. It basically says that when t goes to infinity, what is the probability that the state is in J? And second, what is the limiting fraction of time being in state J? So in the long run, how much time do you spend in J? To calculate these two limits, we have to first calculate the pi I, the limiting distribution of the discrete time Markov chain. It can be calculated from this Pij, the transition matrix for that DTMC. Another is the expectation of surgeon time, which can be calculated from the surgeon time distribution Hi. Then there is a theorem stating that the limiting probability and limiting fraction of time can both given by this Pi defined here. Okay, that's all what I want to introduce in this for this semi-Markov process and limiting theorems. Thank you for your time.